Hello, hello. Hey. I'm on stage right now. Hi. Oh, shit. Okay. So, welcome to this talk about network optimizations, specifically for bigger blocks, but it also applies to other stuff, so it will be interesting to a lot of people, I think. So, my name is Tanguy. I'm sorry, it's hard to say because it's French. I'm a software engineer at Status, that you may have heard of. And I specifically work on VAC, which is our research unit in Status. And more specifically, I work on libp2p, which is a peer-to-peer library. And today, I'll be talking about some of the research we've been doing in the last few months in my team, which is specifically geared towards proto-danksharding, which is one of the next upgrades of Ethereum, actually the next one, which is basically going to bump the block size from 100 kilobytes, which is the current size, to about 600 kilobytes, the bigger block. This extra data will be very useful for layer 2s and anyone who wants to store data on Ethereum. But it's a bit of a pain for me because I work in networking, so I have to push more data through the network, which is never what you want to do. Basically, Ethereum works like this. It's on a fixed clock. I think it's pretty common, pretty well known. Every 12 seconds, you have a new block. And this slot is actually split into 3 parts. The first part is meant to build a block and spread it inside the network. The second part is going to be the attestation, so people voting on a block. And the last part is going to be the aggregation, so basically aggregating the attestations. What it means for us is we have 4 seconds to generate these big blocks and spread them around the network. And 4 seconds might seem like a long time, but it's only 1, 2, 3, 4. So it's not a long time, actually. Especially when you want to spread a block inside a network made of peer-to-peer nodes all around the world with like unknown amount of bandwidth. They are spread over the world, unknown amount of CPU, all of this. And so it's actually quite a big challenge. So Nimbus, which is our Ethereum consensus client, is built on top of libp2p from GossipSub. Sorry, the other way around. GossipSub from libp2p. If you've heard about GossipSub, you go into the Waku talk, which is good. Because the nice thing about libp2p and GossipSub is anyone can use them. And so Filecoin also uses GossipSub, Nimbus, so Ethereum uses GossipSub, and Waku, that you've heard about, probably, also use GossipSub. So I'm going to explain fairly simply how GossipSub works, because it's going to be quite critical. I mean, Ethereum uses this to spread the blocks, so this is the part we want to optimize. Basically, the goal of GossipSub is very simple. You have a network with a few nodes, and one of them has a message. And the goal is to get to this state where everyone got the message. Easy. The way you do this is you have your nodes, and each node is going to connect to random nodes in the network and start to establish a connection. And it's going to ask a few of them, hey, do you want to be my friend? It's going to pick random nodes and start asking for friends. I made this animation myself, as you can tell. Thank you. And so it's going to pick a random amount. In this graph, it seems like you are picking nodes which are close to you, but in practice, you are just picking random nodes. And you're going to need to pick a certain amount of nodes. So in this graph, for instance, the number of connections is about 3 per node, right? Something like that. And this is what we are going to call D. D is going to be the number of nodes you become friend with. And once you are friend with a node, what this means basically is every time he's going to receive a message, he's going to send it to you. And every time you receive a message, you send it to him. So if you start to spread messages in the network, it will look like this. This guy wants to send a message, he's going to send to his friend. Then these friends are going to send it to their friend, etc., etc., etc. So that's GossipSub. Pretty simple. There are more stuff, but this is like the basic of it. Now, we're going to have to put some math into what I just said, so it's going to be a bit boring. Don't fall asleep, please. I mean, you can, honestly, I don't mind. I don't love, yeah. The first thing we're going to try to understand is how much bandwidth are you going to use with your gossip subnetwork. And this one is pretty simple. Every time you receive a message, you forward it to your friends, your mesh. And so basically, the amount of bandwidth you're going to send is payload, so the actual data you are sending, times D. Since we are in a peer-to-peer network, every time you send a packet to someone, it means someone will receive a packet. And so at the network scale, the incoming bandwidth will be equal to the outgoing bandwidth by definition. So that was easy. It's our bandwidth usage. If you try to plug some realistic number into them, so for instance, our blocks of 100 kilobytes that we have today, it will amount to about 160 gigabytes per month per node. And if we just multiply it by 6, basically, you get about 1 terabyte. So this metric is useful because some people actually pay for bandwidth. Like if you are running if you are in Australia or if you are running in a data center or whatever, you might pay for bandwidth. And as you can see, getting closer to 1 terabyte a month is starting to be a bit sketchy. Like it will become harder to join the network because you're going to need more bandwidth and to pay for your bandwidth. And this is like the theoretical perfect world condition. In real life, you have more usage than this, obviously. So that was the easy part. Next, we're going to try to understand propagation time, which is how long does it take to take a message from a single node to the entire network. And the first thing we want to understand, again, I made it myself, as you can tell, is how long does it take to get a message from one node to another node. And here it's basically two parts. You have the round trip time, which is going to be basically the speed of light between these two nodes. It takes time for electricity to reach one node and the other. And the other one is going to be the transmit time. So the first one just depends on distance, basically, between the nodes, more or less. Whereas the second one will depend on the size of the message you are sending. So here in this case, I'm sending a message made of 4 packets. And so writing these 4 packets will take a bit of time on the wire. So again, if we plug realistic numbers, oh no, a bit more math, sorry about that. This is a magical formula you have to use to guess how many hops it will need to reach the entire network. So like, if you send, in Ethereum's case, with 10,000 nodes, D of about 8, it would take basically 5 hops to reach the entire network. So if I send to one people, it's going to send to other people, and in 5 hops, you reach everyone. And so if we just multiply our time per hop that we just calculated with this, we can see, assuming we have 100 megabits per second and 100 milliseconds, whatever, that today it would take 500 milliseconds to spread a block in the network. And if we get blocks which are 6 times as large, it will take 2 seconds, basically. So that's nice. 2 seconds is smaller than 4 seconds. Hey, that was my talk. Thank you. So actually, if we look at the real average today, which we calculated should be 500 milliseconds, it's closer to 1.5 seconds. And there are a lot of reasons for this. It's basically theory versus real life. But the issue is it's hard to know what would happen if we make our blocks bigger. So what we did is basically pay a lot of money and send 3 big blocks on the network. Because today you can already send a big block on the network, it's just that no one does it because it's very expensive. So here you can see on mainnet they send this 1 megabyte block and it costs, oh, I didn't put the price, but yeah, it costs a lot of money basically. So no one does it. I mean, if you know the gas price, you can compute it, but whatever. And so this was a very interesting experiment because we could see what would happen if you would send a 1 megabyte block today, because that's what they did, basically. And it looks a bit like this. I didn't do it myself. Every time you have a red line here, it's a big block. So here also. And this is the time it takes to reach the nodes. And this is the limit of 4 seconds. And as you can see, it's mostly okay, but we still have some outliers here which are above 4 seconds. And so I should mention what happens if you go over 4 seconds is basically that block will probably get dropped. So it's not something you want. You never want that, basically. So that's a bit of an issue, especially in case of attacks. The network will slow down. It's like how GossipSub works. If you start to attack it, it will slow down. The network will grow with time, and as more nodes join the network, it will also get slower. Sometimes you have slow nodes, which are just slow to create a block or whatever, so it will also take longer. And finally, the goal of 600 kilobytes today is kind of a first step, but the goal is to get even larger blocks in the future. So yeah, we're gonna have to optimize GossipSub. But you didn't stay awake during the boring maths for nothing, because now I can show you this graph and you will understand it, hopefully. So the first graph is the effect of D, so your mesh size, on the propagation time and the bandwidth, using these parameters. So you can see that the bigger your D is, your bandwidth is going to grow linearly. So this is the bandwidth per node, because again, you're going to relay a message to more nodes. But your propagation time will kind of logarithmically go down and then go up again at some point. And so we could see that today, as I said, in Ethereum we are at 8, which is a pretty nice balance. We could go a bit further in that direction, but again, in case of attacks, it would be a bit tricky, for the propagation time. This one shows you how GossipSub scales with bigger network, and as you can see, it's pretty cool, because today, as I said, we have about 10,000 nodes. And if we were to go up to 60,000 nodes, in theory, the bandwidth would stay the same, because you're still sending to the same amount of peer, you don't care about the scale of the entire network, and the propagation time grows very slowly, because again, it's logarithmic. So, in theory, we are good on the network size. But we do need to optimize GossipSub, and we basically have two goals for this. The first one is to keep a safe latency. So that means never, ever, ever should a block take more than 4 seconds to be transmitted, even if the network grows, if you have attacks, never more than 4 seconds. And also, it would be nice to keep the bandwidth fairly low so that more people can participate in the network. However, we cannot spend tens of thousands of dollars every time we want to test something. So for the following slides, this is coming from simulations results I got from TestGround, which is a nice software you can use to do the simulations. These are the technical parameters if you're interested, but no one is, I hope. Yeah, so the first thing we're going to try to optimize is for duplicates. So if you look at the GossipSub network, which again, beautiful, I know, what you can see is that each node is going to receive the message a lot of time. As you can see, a lot of links. And this is not optimal for sure, because it means that instead of receiving the message one time, I will receive it like D time, basically, more or less. So as many peers as I have in my mesh, they will basically all send me the message. And also, I will be busy to send these packets or this message to peers who already got the message. So I'm basically wasting bandwidth at this point. But the thing is, it's kind of hard to avoid this, because, for instance, in this case between B and E, they got the message at the exact same instant. And so they started to think, oh, I need to send it to him, and oh, I need to send it to him. But it's kind of hard to avoid this, because you don't know that B already got the message. So I did a simulation just to see the impact of duplicates on the latency and the bandwidth. And I basically used magic, so I was able to access the internal state of other nodes to completely get rid of duplicates. And this is basically what you get. So on the left, you have the latency and bandwidth for duplicates, for a simulation with duplicates, and on the right, latency and bandwidth with no duplicates. So the bandwidth got really nicely slashed, so perfect. But as you can see, the latency is more or less the same. And to get this result, I had to use magic. And unfortunately, we cannot use magic in real networks. So if we were to actually remove duplicates in real life, it would probably increase latency. And as I said in the previous slide, latency is our first goal, because this is like the safety boundary. So it's not that good. If we look at a beautiful graph again, what you can see is that without duplicates, B is going to be very fast to send this message to C, because all of its bandwidth will be focused on sending this message to C. but the first hop, which is sending from A to B DNE, is still going to take the same amount of time, because obviously at this point, no one in the network has the message. And so yeah, the duplicates are nice to avoid like bandwidth, but it will not help you with latency. That's kind of the point of what I'm trying to say here. So we need another solution, basically, and the first one we're going to look at is staggered sending. So the idea of this one is pretty simple. Instead of sending the message to all of your friends at the same time, you send to one after the other. So on the left, you can see A is sending to E, D, and B at the same time, and on the right, is sending first to E, then to D, then to B. And while it will take the same amount of time to send to all of them, as soon as E got the message, he can start to relay it to other nodes. And so it will go faster. Hey, nice. If we do some napkin math, we should see it should get 70% faster according to this random graph, so that's cool. And if we try in real life, it gets 9% slower. So that's not cool. So why is that? It's time for a TCP crash course. Don't fall asleep again, please. I know you just had lunch and everything, but I promise it will be short. So TCP is this protocol we use to connect two peers and send data between them. And the issue with doing that is that, let's say you have two nodes, and they want to talk with each other. They are connected via a link, like probably some wire, some underwater fibers, maybe some radio link, whatever. And somewhere along that link, you have a bottleneck. Yes, I'm French. And so this bottleneck is somewhere in the middle, and what this bottleneck will do is basically prevent you from sending a certain amount of packets in a certain amount of time. So it might be like a slow server, which cannot handle that many packets. It may be your shitty Wi-Fi, like whatever. It cannot only handle so many packets at a time. But the issue is, you don't know where that bottleneck is, you don't know what its size, and its size is constantly changing. So if the bottleneck is a shitty Wi-Fi and someone is watching Netflix on your TV, the bottleneck will constantly change every time Netflix tries to get more video and whatever. So it's kind of a bad situation to be in. And what TCP tries to do is, basically, it's going to send some amount of packets. So in this case, 4 packets at the beginning. And it's going to notice that one of them got lost. So you can see here, disappeared because we have our bottleneck. And so when the second node will tell the first node, hey, I missed one of your packets, the first node is, first of all, going to resend that packet so that the second node gets all of the data. And he's also going to remember that somewhere along the link, there is a bottleneck that can only handle like 3 packets at a time. And if we look at it over time, it looks basically like this. You're going to start your TCP connection, and TCP is going to be very pessimistic about your bandwidth, basically. It's going to send very few amount of packets. And it's going to send more and more and more and more packets until he sees a loss. And when he sees a loss, because you got a bottleneck, he's going to basically reduce his estimate and start this process all over again. And so you get into kind of this sawtooth pattern. And what you call like, I have 10 gigabit of bandwidth, basically means that the average of this sawtooth pattern is going to be 10 gigabits. So that's how TCP works, more or less. But the interesting thing here is this part. At this point, the estimate got to 0, so we got back to shitty bandwidth. And why is that? It's because we didn't send any packet on that connection for a small amount of time. And so TCP, if you stop sending packets, is basically going to say, I don't know anything about this link, let's just say that it's a shitty link. The big issue we have with this is that in Ethereum, as I said, it runs on a fixed clock. And so every 12 seconds, we're going to send the packets. But before that, we may not have sent any data on that link for some amount of time. And so when we're going to send that packet, that connection might be in the shitty state. And it will probably be in the shitty state where you have shitty bandwidths. And that actually explains some of the differences we've seen between the math world and the real world, is that if you just send a message on the TCP connection which has not been used for a while, a few hundred milliseconds generally, it will be super, super slow. But that's exactly what we want to do. We want to send this message as fast as possible on a TCP connection which is basically idle. So we came up with a beautiful protocol to fix this issue. I call it the periodic internet path autonomous probing system, trademark pending. And it's a bit complex, but I'm going to show how it works. Basically like this. And so this fixes the issue, because basically TCP is going to see some packets going on in that wire and it's going to say, oh yeah, perfect, I know this link. This link is very good. I keep sending packets and they never get dropped, even though they're super small, but yeah, so I'm happy. I'm going to keep my estimates. And so if we add this periodic internet path autonomous probing system trademark pending, we can see that finally we got some nice result. Using our stagger send and the while true ping, we got 35% faster to send a message on the entire network. This didn't save a lot of bandwidth, but the latency, which is again our main priority, just got really nicely reduced. Just to be clear, latency is the time it takes to spread in the network. So that's our first optimization. The second one, I didn't make an animation for it, I'm sorry, so it will just be me talking in front of it. Basically, instead of sending a single big message, you just split it in smaller chunks. And it will give you some speedups because it's similar to parallelization, right? Instead of having the entire network focused on spreading a single message, you will have part of the networks focused on a single part, other parts of the network in another chunk, etc. And so, again, this gives us a nice boost. Just going from one message to the same message split in 4 chunks. But again, it doesn't help us a lot with bandwidth. So for bandwidth, we're gonna try to be nice. And we're gonna add what we call the choke message. So if you look at the animation on the right, you can see some very fast yellow packets going on at some point. Too fast, but I was too lazy to do it again. And basically, it's a very small message which is just gonna say, oh, I already got this message, don't send it to me, no need for a duplicate, I already got it. And so while A is busy sending to E, sending to D, sending to B, the other one won't try to send the packet to him. So it's like what we call a choke message, because you're basically choking this connection to say, I don't care about this specific message, I already got it. And so you can see it reduces our pentagram quite nicely. We still have some duplicates, but a lot less of them. So if we put everything together, we have this beautiful graph. We start on the left with our regular gossip sub. Then we split in chunks, which is going to reduce the latency and the bandwidth a little bit. Then we stagger send, which is, sending one after the other. This slashes the latency very nicely and the bandwidth a little bit. And finally, the choke message, which is basically going to reduce our duplicates in half and speed it up a little bit, but not that much. So all in all, we got for free, because I had to work on it, so it's not free, but for free. Basically, we reduced our latency and our bandwidth by half. But I have to say that these optimizations are very specific to big blocks. Because if you are sending a very small message, basically the transmit part of this delay per hop, which was in a few slides back, is going to be so small that it will be harder to optimize. But in the case of bigger chunks, which is what bigger messages, which is what we are interested in, we get these nice results. So actually, these two first, so obviously gossip sub, but the splitting in chunks will be part of the Ethereum next upgrade, so you will already have this kind of boost in latency and bandwidth. And the other ones are going to come along. Choke message is probably going to be in a few implementation by then also. Stagger send is the most complicated one to implement for a reason I won't go into. So it will probably come a few months after the upgrade. I forgot my next slide, so let's just switch. Oh, right. All of this mess was just to get from 100 kilobyte message blocks to 600 kilobytes. If you want to see this talk tomorrow by Chaba, he's going to explain how was I going to switch from our puny 600 kilobytes to 32 megabytes, which is another story. But yeah, actually the optimization I showed you just before should enable us to get blocks up to a few megabytes, but they are doing what is called DAS, so data availability sampling, which is really going to get the blocks even bigger. So check out that. I know it's during lunch, but you can skip lunch. That's okay. Another nice benefit is that, as I said, all of these optimizations are going inside Gossip Sub. And Gossip Sub is not only used by Ethereum, but also by Waku, by Filecoin, and by, in a way, all of the people building stuff on top of Waku, Ethereum, and Filecoin, which is to say, everyone, right? So that's the really nice thing about sharing this piece of infrastructure, is that we can spend time improving it, and everyone will benefit for free. Again, I had to work on it, but as far as they're concerned, it's free. I was not the only one working on this. There was Jacek from Status, who basically started this whole adventure. Anton from Consensus, who helped me with simulations and bouncing ideas and all of this. And myself from Status, that you already know about. Yeah, that's it. Thanks. I do have to do my plug. So if you want to check VAC, which is our research team, you can see the website here, or you can scan this QR code to join our Discord. And if you have questions, you can ask them here, ask them by email, ask them anywhere. I'll try to reply. No questions?
Wouldn't the staggered send potentially make it a little bit easier to attack the network, though? Because if you're relying for that for a large latency gain, you take out a few core nodes, that latency can spike up a lot faster, and then you'd end up with this synchronization problem.
Yeah. So I'm gonna go back to my. Yep. Where is it? Too many slides. Yeah, so staggered sending is not for free. I went a bit quickly over that part, but basically if A is a bottleneck, it's a really nice improvement because you're going to get this speed up. But if A has like infinite bandwidth and E, D, and B have like limited bandwidth, A could send the message to all of them at its full speed and it would actually be faster. So staggered sending in general is only gives you a benefit if you are the bottleneck, which is less ideal than what I just said. But basically, staggered sending optimized for the worst case scenario, which is you are the bottleneck. In the case where you are not the bottleneck, we will have a bit of losses, but nothing crazy. And it's the same thing in case of attack. I won't go into the details of how staggered sending works, but basically A can detect the bandwidth of E, or compute the bandwidth of E. And so if E is super slow, A might want to prefer to sending to someone else, which is not an attacker, basically. But yeah, this first version will be a bit simpler than this, which again will have some losses in the best case. But again, our goal is not to get all the time faster, it's just make sure we are still below 4 seconds. Did I answer? Okay.
Most of the optimizations you have mentioned are for TCP transport, right? But libp2p is supposed to be agnostic to transport. So are there any optimizations being done for other transports as well? Or like maybe to rather rephrase, would some of the same optimizations work for like Quick or web transport or some other transports?
Yes. So the TCP explanation I did is actually quite a common way to handle this kind of protocols. So Quick works in the same way. WebRTC, I'm not sure, honestly, I don't really remember how it works. But it would be beneficial for all of these. Quick, it might be a bit simpler actually to use Quick, because Quick is not in the kernel, it's in library, right? And so you could just say to Quick, hey, stop doing that stupid thing where if I don't send a message, you give me shitty bandwidth. You could just disable that flag. But because TCP is in the kernel, we have to use workarounds, let's call. to make it work. But for sure, it would also help with other protocols.
Thanks.
When you're talking about bandwidth measurements, I assume that when you have this kind of topology of nodes, right, does the node send between them some kind of control messages? Yes. So when you're talking about bandwidth measurements, these kind of messages are taken into account or not?
It may not seem like it, but this is a very complicated subject, and like
Yes.
bandwidth measurement is the reason why stagger sending will be the latest one to be added to this. But in practice, yes, control message would be supported. But as I said, like the issue with bandwidth is if someone starts to watch Netflix on your TV, your bandwidth will change, and so it might be counterintuitive, but it's basically as best to try to compute the bandwidth of this single link or all of your link, because no matter what, these links will be shared with other people, and so you have no way to know like what other people are doing. But yeah, bandwidth measurement is a really big complexity of the system.
Okay. Thank you.
Thank you.